All right, today we're going to talk about colligative properties of solutions. So really we have three targets that we're going to be working on today. We're going to be thinking about really the conceptual thing of what happens when you dissolve a material, a solute, into a solvent. Now we know how solvents behave as a pure substance. We talked about liquids having IMFs, how those IMFs change as you either freeze or as you boil. And what we're going to see is that when you dissolve something into a solvent, so forming a solution, you actually change the properties and deviate them. Okay? Also on your targets, we're going to be using some calculations to do this. We're going to talk about the conceptual portion of this today, and then next week on Monday we'll actually look at the calculations and do those together. Okay? So let's define what a colligative property is. So the word colligative means a property that's going to change depending on how much you put in, but independent of what that thing is. So what this means is that if I have a pure solvent like water, it has a boiling point, it has a melting point. If I mix something into that water, I change the melting point and the boiling point. The amount it changes by, so if the boiling point increases or decreases, the freezing point increases or decreases, it's solely based on how much we're actually dissolving in, not on whether we're dissolving one ionic compound or another, one covalent compound or a different covalent compound. So we're going to be looking at the factors that affect this and which direction these changes actually go through. Okay? So let's think about what happens when something dissolves. When you put a substance into water or any solvent, we'll use water as a good example, we know that the substance will form intermolecular forces with that solvent. So in the case of water and a polar covalent substance, we form IMFs based on dipole-dipole and hydrogen bonding, and that allows the substance to dissolve. We also know when you put something that's ionic into water, it's going to dissolve because ionic compounds are polar. But we also know that ionic compounds do something as well. They don't just dissolve, they also dissociate, which means they split apart into their ions. So you have the individual ions floating around in the solution. Okay. So dissociation is a topic we spent a lot of time talking on this past week. It's something that's going to be popping up in an application again today. So here is what happens. So these are the two big ideas. Okay. When you dissolve a solute into a solvent, you change both the boiling point and the freezing point. And by boiling and freezing points, we mean temperature. The temperature at which these changes occur. So if we're looking at the freezing point, when you dissolve a solute into a solvent, making a solution, that takes the freezing temperature of the pure solvent and actually lowers it. We call this freezing point depression. Depression means it's going down. So freezing goes down, and really this has a lot to do with IMFs. You can imagine if we have pure solvent, so water, if I go ahead and try to get this water to freeze, I'm strengthening the intermolecular forces, okay, to make that happen, going from a liquid to a solid. However, if I put something into that water, it's going to have an effect on the ability of water to form those IMFs and strengthen them. So if I have salt in water, by adding the salt, now it's harder for the water molecules to come together and form those stronger IMFs. The salt gets in the way, so to speak. And so I can still form those IMFs, but now I have to remove even more energy from the system. And what that means is that it actually takes a lower temperature to freeze it. The best example of this is when we take icy roads and put salt on them. The idea is that the salt doesn't heat up or melt the ice that way, but what it does is it prevents the pure water, the ice, from staying a solid. When you mix the salt in, it actually dissolves into the ice and lowers the temperature necessary for that material to remain a solid. And so it interferes with the IMFs and allows the water, the ice, to melt. Okay? The other end of this is the boiling point. So boiling point elevation means when you put a solute into a solvent, you take the boiling point of the normal solvent and elevate it, so it's going up. And again, we can see this based on intermolecular forces. If we have a liquid like water, we know that to boil it, we're weakening the IMFs. We're essentially separating and pulling the water molecules out of the way. if I do that, but put a solute in there, like salt, what happens is now we still need to break the water's intermolecular forces, but now the salt, again, gets in the way. It's going to interfere from the ability of these water molecules to leave. These, it's easy, but this, it's much harder to do. It forms some new intermolecular forces. And so we can still boil it, but now we have to take that temperature and make it higher. We have to add more heat for this process to occur. So this is why we put salt in pots of water when we boil them. It doesn't speed up how long it takes for the pot of water to boil. It actually makes the water boil hotter, and therefore your food cooks faster. It's cooking at a hotter temperature. Okay? Now the equation that we use for this is the Kimi equation, which I have here. The Kimi equation is delta T equals Kmi. Now we're familiar with a lot of these variables. K is a constant. If you flip your notes over to the back, you'll see that there's a table of different K values. You'll see KFs and KBs. KFs are for the freezing point. KBs are for the boiling. You'll notice all the KFs are negative, all the KBs are positive. So this depends on the solvent, not the solute. Okay, so this is a constant based on our solvent. Little m, we know from this week, is molality, moles per kilogram of solvent. So the more you have dissolved in your solution, the bigger the molality and greater the effect. We know that delta T, delta means change, this is the change in temperature. If it's positive, it means we're elevating the boiling point. Negative, we're lowering or depressing the freezing point. I is something called the Van Hoff factor, and Van Hoff factor is basically a fancy word that says how many pieces do you get when you dissolve something into a solvent. So for covalent compounds, this value is 1. So a covalent compound, and I can use ethanol or sugar or any covalent compound, when it dissolves, it can't break into anything. It doesn't have any ions to dissociate into. So when I put one molecule in, I get one piece. That's it. I is 1. With ionic compounds, then we have to look at what we get when we dissociate it. So if I put sodium chloride in, it dissociates because it's ionic. So what do I get? I get a sodium ion and a chloride ion, one of each, total of 2. Put one sodium chloride in, get 2 ions, 2 pieces. If we look at another ionic compound, magnesium nitrate, dissolve that in, dissociate it because it's ionic, I get 1 magnesium ion and 2 nitrates. 1 plus 2, 3 total pieces. We can get a little bit crazier with something like calcium phosphate. When you dissociate that, you get 3 calcium ions and 2 phosphate ions, grand total of 5. So by working at the dissociation equation, we can figure out how many pieces it'll break into. Again, if it's covalent, it's always 1. Doesn't dissociate. Ionics, it'll always be 2 or more, however many ion pieces you get as a result of this. Okay. We'll look at the calculations like this on class on Monday. The big ideas we've been talking about is the conceptual part. It comes down to things like intermolecular forces, changing the ability of us to break those intermolecular forces, and then concentration. Again, colligative property means that it changes the amount depending on how much you dissolve in. The more you put into the solution, the greater the effect. The higher it'll boil, or the lower temperature it'll take to freeze.